To understand the relativity theory, light is the key. Light is very fast. In fact, it travels at close to 300,000 kilometers per second, which is how fast I usually last in bed with my But light is special. Because the speed of light is constant, it stays the same no matter who's observing it. Let's say you're on a plane, and suddenly you need to release some diarrhea. So, you get up from your seat and run toward the toilet, while producing some very unpleasant smell along the way. Now, for the passengers who are unfortunately stuck on the same plane as you, your speed is simply the speed of you running. But for me, who's watching it happen from somewhere far away with the telescope I bought on Temu, your speed is the speed of you running plus the speed of the plane. This is what we observe in everyday life and how physics should work according to Isaac Newton. Basically, speed plus speed equals more speed. However, this does not apply to light. Now let's say you stop running and turn on a flashlight. Flashlight, and point it straight ahead. To you and your fellow passengers, the speed of light of your flashlight is the speed of light. But to me, the speed of light of your flashlight is also the speed of light. In other words, for me, the speed of light does not become faster despite being on a fast-moving plane. How come? Well, I don't know, nor did Einstein. It's actually one of the great mysteries of our universe. But it is a fact, and it has been confirmed in many experiments. However, when Einstein first came up with the relativity theory in 1905, the constancy of the speed of light was just a theory, which means the relativity theory was also just a theory, which is why our dude was never given a Nobel Prize for it. Anyway, just remember this. For the relativity theory to be true, the speed of light must be constant, no matter the observer. Now, let's do a little thought experiment. Let's say you're no longer running with diarrhea on the plane. Congratulations. Instead, the plane is empty except for a light clock in the middle. It's made of two mirrors, one on the top and one on the bottom. And the photon, which is the smallest unit of light, bounces back and forth between them. For argument's sake, let's assume it takes the photon exactly 1 second to go from the top to the bottom, and vice versa. So, the speed of light, in this scenario, is the height of the clock per second. Now, if the plane stays still, the photon travels along a vertical path, which is the height of the clock. Pretty obvious. However, when the plane moves, the photon will travel along a diagonal path, which is longer than the height of the clock. So to an observer on the ground, when the plane moves, the photon travels a longer distance. Now, let's say the plane starts moving as soon as the photon leaves the top of the clock and stops as soon as it reaches the bottom. You, who are now observing the plane with me, and your pants still smell by the way, will see that the photon move along a diagonal path, longer than the height of the clock. You're also timing the plane's trip with a fake Rolex you bought on Temu. And here's the question, how long did the plane travel? 1 second, which is the amount of time for the photon to move from the top to the bottom of the clock? Or longer? The answer is longer, which is also what she said when I showed her my Because remember, the speed of light is constant no matter the observer. So for me and you, the photon still travels at the same speed, which is the height of the clock per second, despite being on a fast-moving plane. And here's the problem. The speed of the photon, aka the speed of light, is the same, yet it travels a longer distance. And time equals distance divided by speed, so by pure math, it must have taken the photon more than 1 second, say 1.025 second, to go from the top to the bottom of the clock. But for the person on the plane, let's say your cousin, it still takes the photon 1 second to complete the trip. Therefore, the time on the plane, relative to me and you, must have slowed down. This is called time dilation. Relative to the observer, the faster an object moves, the slower the time passes for that object. So, now you can finally understand the twin paradox. Say you have a twin. You hop on a spaceship and start circling around Earth at extremely high speed, while he stays back at home because he's a loser. To him, your time passes slower, and to you, his time passes faster. You then take a look at your fake Rolex, and you're like, oh shit, it's only been 5 minutes, and Katy Perry's already too insufferable. So, you ask the pilot to slow down and take you back home. But hey, it's already 30:25 on Earth, and your twin is still alive, because turns out he's the emperor of mankind. Warhammer 40k? No? Anyway. Now we're done with time dilation. Let's talk about girth. Length. Let's go back to our plane example. Say you and I see the plane move from point A to point B in 1 second. So for us, the distance the plane travels, let's call it AB, equals the speed of the plane times 1 second. But we also know, due to time dilation, the time on the plane passes slower. This means, for your cousin who is on the plane and who is very lonely because his girlfriend dumped him last week, it takes less than 1 second for the plane to move from point A to point B. That is, for him, it takes less than 1 second for the plane to travel distance AB. But that doesn't make sense. You see, the speed of the plane didn't change, and for your cousin, the plane traveled for less than 1 second. So for him, the distance the plane traveled should be shorter than distance AB. A paradox. So how do we fix it? Easy. Let's label things. Let's say before the plane moves, your cousin is at point C. When the plane stops, he's at point D. From our perspective on the ground, distance CD is equal to AB, the full distance the plane travels. Now, here's the fascinating part. The moment the plane starts moving, everything on board, including your cousin, contracts slightly in the direction of motion. It's like the whole plane gets a little squished. So now, your cousin is no longer exactly at point C. He's slightly ahead of it and closer to point D. Then the plane keeps moving and it stops. As soon as it stops, the contraction disappears and everything snaps back to normal size. And look, your cousin is now exactly at point D, just like we expected. But what about the distance he traveled? It's not the full CD. Actually, it's from a bit ahead of point C to point D, which is slightly shorter. In other words, your cousin traveled for less time, yet the speed of the plane stays the same. Therefore, he must have traveled a shorter distance, and to achieve that, the plane must shrink in length, just like your So, to sum up, the speed of light is constant no matter the observer, and the faster an object travels, relative to the observer, its time slows down and its length shortens. Teacher! Yes, Mr. Sausage? Does that mean if I hop on a rocket, as the rocket accelerates, relative to you, I become slower and shorter? But when the rocket slows down, relative to you, I become faster and long... Shut up.